Good morning, Preeti ma'am. Preeti ma'am, can you hear me? Good morning, participants. I'll just get connected with our resource person, Dr. Preeti Sharma. And as soon as we receive a communication, we'll start with the session. Good morning, Preeti ma'am. Participants, please give us another 5 minutes as we got a confirmation from our resource person, Dr. Preeti Sharma. She has some problem with the network connectivity, but she's restarting her computer and she's going to get back to us. Ma'am, is everything working now? Yeah, good morning.
Hello?
Can you hear me? Dr. Preeti? We can hear you.
Hello?
Can you hear me?
Yes, I can hear you now.
Yes. That's great. Good morning, Preeti ma'am.
Good morning. I'm sorry for the technical glitch there.
That's okay. It's all part of the show. And are we good to go? Shall we start
Yes.
the session?
Yes.
All right, great. Namaskar, very good morning to all the participants and our eminent resource person, Dr. Preeti Sharma. Ma'am, we welcome you to day 3, session 1, 2, and 3 of STTP phase 3 on econometrics. Thank you so much for joining us today and welcome to the participants for day 3, session 1, 2, and 3 on STTP econometrics. Our eminent resource person today is Dr. Preeti Sharma. She's an associate professor and dean of administration in IIT Indore at discipline of economics. She has done a PhD from IIT Bombay. She has published more than 40 research papers in national and international journals. She has some excellent publication. I think if I go on the whole day about her achievements, it would be very less. Preeti ma'am, thank you so much for agreeing to be a resource person in phase 1, 2, and 3. And we are very lucky and we are extremely privileged to have you on board. The dice is yours, ma'am. Please proceed with your session.
All right. Thank you, Dr. Pallavi. I always keep saying this to Dr. Pallavi. Don't say that you would continue to go on and talk about my publications and all. I'm just a simple researcher, like many of you. So, and I'm also almost always, I can say, forever in my life, I will continue to be a student. And I keep saying this in my all my econometrics classes that I am not an expert in econometrics. I just apply econometric tools. So I am basically more comfortable with few parts of econometric analysis and the subject or course as such. So please bear with me if I am not able to clarify things on all aspects which you may be wanting to know about. All right. So to begin with, what I would like to do is, I would request Dr. Pallavi to let me share my screen. I will use a whiteboard and I will kind of scribble on that
Ma'am, I
board.
have already given you the rights, and what we do every time, I'm going to continue with that as well. In the first day of our session, we have covered what is econometrics, the anatomy, the methodology, as well as some part of regression, which basically involved the classical linear regression model. And yesterday we have covered some part of time series analysis. So this is what has been done till now. And as I informed the participants yesterday, we are going to take up panel data and then again fixed effects and random effects. Thank you so much, ma'am. I think you can continue.
Right. Thank you. Thank you, Dr. Pallavi. So are you able to see the blank screen now, which is the whiteboard?
Yes, ma'am. Whiteboard is visible.
All right. So as you have been already, told in your introductory lectures that what is regression and what is the, why do we do that? And you might be already, as I have been informed already, that most of the students are from economics background. So most of you might be already aware of the basic differences between what is covariance, what is correlation, and what is regression and what is causation. So all these four different things are what we need to know beforehand, and therefore then only we decide that, okay, at what stage of our research do we want to do a regression analysis. And in order to do the regression also, what are the reasons behind that, and then we also move on to the causation reasoning. And after doing all those basic understanding about what your research problem is and what your research questions are, and to address those research questions, you will be identifying that what are the different variables that you are going to include in your analysis, and based on that, that what kind of variables you are going to use. You would also want to then know that what would be the kind of relationships that you want to analyze. And while doing all of that, you might have already learned that in case of regression analysis, in simple regression analysis, ordinary least square method, how do you identify that what would be a dependent variable, and you would also identify that what would be the independent variables, or would it be a single variable which will be affecting your dependent variable, or would there be multiple variables which are also called your explanatory variables, which will affect the dependent variable. Once you have reached that kind of stage, then there are two things that you would be doing, and perhaps a part of which has been already done, and maybe some part has not been yet covered by the previous speakers, is that when you are doing the regression analysis, what you do is you have two situations. One situation is where you undertake regression analysis, which is for one cross section. All right. So you know what is cross section. So cross section is when you are analyzing the impact of one or more variables on one dependent variable in a given time period. Now, when you're doing that cross section, what you may do is you may include several entities, that is several cases. Often in our in our analysis, when we are entering the data, each of those rows which represent each entity are also often known as cases. So what we do is we first note down the explanatory variables and we observe the phenomenon. Phenomenon is the what is happening on the dependent variable. Phenomenon is the dependent variable. So we observe those. And when we are doing that, when we are doing it for several entities for single time period, that is cross-section analysis. Then when we are, so what I can write here also. All right, so as of now, I have already, and maybe you might be already aware of this, is what you do in the cross-section analysis. So in your cross-section analysis, you are identifying that what will be your dependent variable, which is a function of your independent variables. It can be one variable or it can be several variables. So for that, what you do is you note down values for case 1, which is for your y, and for your x, say x, if it is more than one variable, independent variables, then x2 like that. So you note down the values for this different, for this entity or this case on all these variables and their impact on the phenomenon variable or the dependent variable. So then what you do is case 2, you enter the information data which you have gathered. Like that you do. And when you analyze this, what you are doing basically is, through your regression model, ordinary least square simple regression or multiple regression, is cross-section analysis. Now, then you have been already introduced to another thing, that is the time series. Now, in case of time series analysis, what you're doing, basically, you are having only a single case, all right, or your entity will be only one. And you're going to observe these same variables, which are the explanatory variables and the phenomenon variable for this case over different times. So you have T0, T1, T2 like that. So you are going to note down for this particular entity that what will be the values of different independent variables. You note down those. So here when I was noting down, I was noting down in this direction. And here when I'm noting down in this direction. Now, this is what is going to give you the time series analysis or results. Then when you combine both of these, that is what is called panel. So now in panel data analysis, what is going to happen is that you will have case 1. Here will be your time. Maybe we can start with T1, T2, T3, like that. Case 2, T1, T2, T3, like that. Here will be the values of explanatory variables. And here will be the value of your dependent variable. So when you have this kind of your data set, what the analysis that you would do is panel data analysis. Now, in order to understand this, what we do is, see, we have the simple situation, which is where you have, first was your cross section. So to represent the cross section, what you will do is you will have your yi, which is for a specific entity or case is equal to, for example, we are writing it here as alpha plus beta xi plus your error term. Now, in your time series, what did you have was you have your alpha here plus beta, plus your error term. All right. Now, in your panel data, so this is your cross-section data, this is your time series data, and so for your panel, what you will have is YID is equal to alpha plus beta XIT plus your error term with IT subscripts. Now, when you have this panel data, what you will be facing, just the way we talked about regression, will be having these options as depending on what kind of research you are doing and what kind of data is available. So you do either cross-section analysis or time series analysis or panel data analysis. Now, when you have panel also, then you have choices. So what are your choices is that if you are going to analyze where a situation where your this, in case of panel data analysis, your intercept term is the most important component. So we are going to do everything around intercept term, although there is a lot of work which is related to the slope term also. But for this session, we are going to restrict ourselves only to the to what we are going to do with the intercept term. That is what we are going to deal with. So intercept term and how we are going to address the concerns related to intercept term. So if based on our review of literature and based on our data, based on our understanding, if we can assume that the intercept term for all the entities in the panel for all time periods is assumed, if it can be assumed to be same or given or constant, then what we do is then we can use pooled OLS. All right. Now, if we are going to do that, then in case of undertaking the pooled OLS also, what we are going to do is we are basically assuming here alpha as constant, and that is why it is also known as constant coefficients model. All right. Now, when you're going to do this, assume that your alpha is constant, then you're going to apply the constant coefficient model or pooled OLS regression. All right. Now, in case of you have other options also within the pooled OLS model, and that is that you will have to assume that all the explanatory variables are strictly exogenous, and we are going to do all those in detail. But right now, what I'm telling you is the overall picture of what are the options that are available when you do panel data analysis. Now, the other situation which can happen is that where your intercept is, so this was here, it was assumed to be same, and what are the options or what will happen when your intercepts are different? Yeah. So now, if your panel, if your intercept term is going to be different, then you will be having two choices. One is your fixed effect model, and second is your random effect model. Now, what you're going to do is here that within the fixed effect model also, what are the options that you would, what are the kinds of analysis that can be done is, number one is you can do within group fixed effect model. You can do, you can adopt first difference fixed effect model, and you can adopt least square dummy variable model. Okay. Now, what we will do these, we will see how, in what situations we are going to use those differently. Now, in case of fixed effect model, what the basic difference between the fixed effect model and the random effect model is that you are considering, number one is you are considering the alpha to be different, all right, which is your intercept term to be different. But in case of fixed effect model, what we do is we take that the intercept term is different, but we also understand that the representation of that alpha for the entire panel is such that we do not bifurcate it for different time periods. All right. So what we are going to do is, in case of fixed effect model, that is what we are going to do with alpha. In case of random effect model, what we do is we bifurcate this intercept term. We understand that there is a component of randomness in the intercept term, and we adjust it with the error term. We will see we create an entity, a factor which is also known as the composite error term, and we will do that one by one, and how we are going to apply that. All right. Now, first, so what we do is, in case of what we saw in the previous board, was that we were doing so in the first board we were seeing that how we are going to do the pooling or the pooled OLS. Now, basically in case of pooling, what we are doing is we are identifying the We are doing pooling of independent cross sections. All right. So basically what you do is you may have a data set where you have cases 1, 2, 3, 4. All right. So you can have two situations. One is where you can have cases like 1, 2, 3, 4. Cases 1, 2, 3, 4. And for these, for different time periods, T1, T2, T3, like that. For this also T1, 2, 2, 3, 3. For this also like that, this also like that. Now, this is one situation. In this situation, what is happening? In this situation, your data is for this particular case in time period 1, for the same case in time period 2, for the same case in time period 3. Your information, your data is on dependent and independent variables on this particular case. So you are continuing to observe those phenomenal variables and impact of independent variables on this particular case. Then on this particular case also, again, you are observing data in time period 1, 2, 3, 4, like that. And then in this particular case. Now, sometimes what happens is, sometimes you may be having a panel where you are going to have data for time periods T0, T1, T2, like that. But what is going to happen is, it is not necessary that for T0, the cross section, the case which you are taking is the same. Whereas what is going to happen, it is possible that these cases may be different. You are observing the same phenomenon. You are observing the same phenomenon. You are taking note of the values of x1, x2, x3, like that, right? But this case entity may not be the same. These entities may be different. All right. If that is the case, where these entities are different, then what you do is known as pooling independent cross sections. All right. Now, you can also do the policy analysis with panel data. All right. Now, what you are basically going to do in the pooled cross section, you have already seen that these cases may be different. But in case of when your data is such that the case is same and you are observing the same cases over a period of time, this is the situation where your analysis will be exactly panel analysis or panel data analysis. Okay. Now, in case of pooled cross sections, so you understand now the difference between pooled cross sections and the panel data. Oftentimes, it may appear to be same because there are time components and there are separate entities also. But please remember that those entities may not be the same. Then you are going to use pooled cross sections. All right, and pooled cross sections are many times used when you have very big or very large samples, and you want to what you want to investigate is the effect of time. All right, can anyone tell me that think of an example where pooling independent cross sections kind of analysis can be used?
Population.
I'm sorry, I could not hear you.
When we do the population census.
No, population census would include entire population. You have to you have to come to a kind of, see, we are going to apply here. This can be done where we are drawing. That is the difference between when we cannot survey the entire population. Yeah. So what was your, you wanted to explain something?
We can take the example here, the last 20-year financial performance of a specific industry, just like a pharmaceutical or any other. We can use here pool.
Where the entities may not be same.
Yes.
Yeah. Okay. Another, very commonly used data where we use the pooled cross sections analysis is also when you are utilizing large data which is collected by NSSO. So because what NSSO does is NSSO collects data from very large sample, and oftentimes it is repeated. So there are several time periods on the same variables, but it is not necessary that the entities or the households which have been covered in the previous survey will be the same in this survey. The information collected may be the same, but not the households. All right.
Ma'am?
Yes.
Actually, I have a question. Can you give an example of the entities, different entities and same entities?
Yeah, so this is the example where I'm talking about, say, if when, say, the National Sample Survey Organization conducts the surveys and they collect the data and researchers utilize those data, that is more of a pooled cross-section. We can conduct pooled cross-section analysis there. Why? Because when, so here what NSSO is doing, NSSO, say, suppose there are several households, all right. For example, this is the, wait. So, for example, these are our two sample spaces, all right. So this is the set of population from where we are going to draw the sample. So this is A, or we may not say A and B. If it is same, then depending on what method is being used. So suppose that from here we take 1, 2, 3, 4, like that, 5, 6, there are 10. Okay. From here, if suppose out of these 10 individuals, suppose we draw a sample of 5 individuals. All right. Now, in the time period 1, first time period, if we select 1, 3, 5, like that, these candidates or these units. So in time period 1, our units which we are selecting is 1, 3, 4, 6, 10. Okay. Now in time period 2, for example, what we do is we collect the information about same data from different individuals, that is, say, 2, 5, say 9, like that. And suppose this pool is very big, so it is not necessary. There can be repetitions, but it is not necessary. So if like that, now what is happening here is that we have the information about the same variables, all right? But what is happening is that the case, that entity is not the same, all right? So in those cases, we use pooled cross sections. Whereas in our panel data, what is happening is, in the panel data, if the surveyor has interviewed, say, my household, then, for example, this survey is conducted annually. Okay, so every year, if my household is surveyed, and so then I am the case one, and consistently the data will be collected for time period 1, 2, 3, 4 for my particular house. Suppose then the surveyors also survey Neha's household. Then Neha's household is surveyed every year. Then suppose that it is for Mr. Pradhan's household. Like that, if the same household, same entity is continued to be surveyed or analyzed, or their data is utilized, then that is a panel. Whereas here, this is pooled cross-section. Is that clear?
Ma'am,
Yes, please.
ma'am, this is the reason then where we have different intercepts.
No, intercepts, we will deal with that differently. Yeah, here also intercepts will be different, because what we are doing is basically we are treating each time period, each entity as different. Why? Because what our target in case of pooled cross section is to see the impact of time. All right,
Yes,
and we do
yes.
not worry so much about the entity itself.
Yes.
Whereas in case of panel, we want to see both the things. We are giving importance to the time, how
Yes, ma'am.
time is impacting individual entity.
Yes, ma'am.
So we are paying attention to time as well as entity.
Okay,
So,
ma'am.
ma'am, we can say that panel data is superior than cross-sectional.
Yes, of course it is superior then. But in many cases, especially if you are analyzing some kind of big policy implications, say development policy or some government policies, then it is very difficult to get the panel data. So panel data, it is easier to analyze panel data for when you are doing it for state, for countries, for districts, because then it is easier to get data for a district statistic over time. But if suppose you are going to see the impact of a certain kind of pension policy, or unemployment benefit policy on the households. Now it's a huge pool, and every time tracing the same individual is difficult, is impossible. So in those cases, we can still see the impact of those policies on those kinds of households, basically, and not exactly that particular household. All right.
Ma'am?
Yes.
Ma'am, so in case of pooling, are we selecting different cross-sectional units randomly, or we're deliberately doing that?
No, randomly. We do it randomly.
Okay, ma'am. Okay,
Yeah.
thank you.
Yeah. Okay. So,
Ma'am, just a question. Why we are saying here the panel data is superior than the cross-sectional?
why we are saying panel is superior in the sense that you will be able to see the individual entities, specific characteristics also. Those will also be able to play a role. Whereas in case of pooled cross sections, because those entities are different, so the component which is specific to the particular entities, that doesn't get analyzed.
Comparison
but the characteristics of the panel and the cross-sectional. So in the panel, it's including the time series as well as cross-sectional. So
Yeah.
both the characteristics of both the data is little different. Na? A specific
Yes,
point
yes,
of time cross-sectional. So how
Yeah.
we can say
we
superior?
can't say superior, or in fact we can't say superior. It depends on what kind of analysis we want to do and what kind of data is available. So I agree with you that we can't say that which one is superior. it would be easier to make more clearer statements about the role of certain factors in case of panel data compared to pooled cross section. In case of pooled cross section, our focus is on time, impact of time, right? So
Yes, yes, ma'am.
and but there is a good thing also. So there is a pro as well as there is a con. The good thing or the merit about pooled cross section is that you can have a large sample, and the demerit is that because individuals are not the same, so you will not be able to say things very confidently about specific components of those individual entities. Whereas in case of cross section, it is like you can say more definitely with those, but the panel data cannot be of the size which pooled data can be. All right. Now, so how do we utilize this in case of policy? We have already seen that what we can do is you can simply compare the change in outcome across the treatment and control group. So basically, in order to do the policy see the impact of the policy, what you can do is you compare that you see the outcomes, or you see the outcomes across treatment group and control group. So that is what we do, right? In all, basically in our experimental design, what we would have been doing is that we understand that in all our natural sciences as well as in social sciences, when we are mimicking those, is that there will be a control group and there will be a treatment group. So, and we see that the control group is the one where the policy change is not applied, and treatment is where the policy is applied, and we do a comparison of these, and we see that we estimate the impact of policy, right? Now, so now now what we do is we can, if we have to analyze the data when there are only 2 time periods under consideration, and we want to make a comparison between those 2 time periods, then we can utilize a method which is called difference in differences. Now, in case of difference in difference in differences, what we are doing basically is that we are going to identify a dummy, and we see that I request everyone to please keep yourself on mute. So what we do is, in order to see the impact of the policy, what we do is we create a dummy which will correspond to the to having the policy and not having, or where the policy has been implemented and where the policy is not implemented. So in that case, what we do is we create that dummy variable which is for post policy change, and we also have the difference in difference estimation. We will see all of that one by one. All right. Now, So before we do this in detail, let me go back to what we were discussing about the intercept term. All right. So what we can do is, in our analysis, oftentimes you might have already done this perhaps, is that when we want to analyze the causation, when we want to see that what is the causation effect, then basically we take the lag values of the explanatory variable or variables to see that which of those are causing the change in the dependent variable. All right. Now, so we can use, in case of panel data, we can use distributed lag models. All right. Now, when we are doing either distributed lag models or the other panel kind of analysis, one thing that we want to talk about the intercept is that the intercept also can have two components which will be affecting the dependent variable. And what are those two components which affect the dependent variable is that one is the component which is called time constant component, and the other is known as time varying component. All right. Now, when you are writing your intercept term in your equation, what you do basically is you represent it with alpha I or AI. All right. Now here, this, what does this show? This shows that there is no T subscript. All right. When there is no T subscript, what it means is that we are considering it to be a time constant component of the intercept. All right. Now, this intercept is the main important component of the entire panel analysis, and therefore, and this intercept is what takes care of the, or explains the heterogeneity of individual entities with respect to time, and when we are keeping the time also constant. So this component is going to tell us two things about the entities. One is the time constant unobserved component, as well as time varying unobserved component. So that is why panel data analysis is also known as unobserved effects model or analysis. All right. Now, the important things that we continue to do around is about this intercept term. Now, this intercept term, what are the main components or main criteria that we are going to consider when we are doing panel analysis is that we need to know that what is the correlation between your intercept term with our independent variables. All right. Now, it is expected that the correlation between the intercept term and the individual explanatory variables should be equal to 0. And what it means is there should be no correlation. When we understand that there is no correlation between the intercept term and our independent variables or explanatory variables, then what we can say is that our estimator is unbiased and consistent. All right. And what does that mean is the covariance of the XIT with the error terms. The other thing is this is equal to 0. This is the second thing. And then we also want to see that if we combine the intercept term with the error term, combine the intercept term with the error term, then what is going to happen is we are going to create what is known as the composite error term. And this composite error term can be written as BIT is equal to mu IT plus AI. All right. Now, in such a case, what we can do is that differencing, I started with that here. Here I had started with that. So the differencing technique. So the differencing becomes a powerful technique, and that can be utilized. First, we see in case of 2 time periods. And this is also known as the difference in difference estimator for a 2 time period panel data. We will see how we do that. All right. Yeah. So what we are going to do is how we are going to the assumptions which we have discussed just now in the last word. We will see how we are going to apply those. All right. So the assumptions for pooled OLS using first differences. Now, so for what we are going to do is for each I, that is for each entity or case, we know that the model is YIT is equal to beta beta 1 XIT plus beta k XIT plus, this is our intercept term, plus the error term with time component. All right. Now, if we are doing what I was talking about, policy analysis, If we are doing policy analysis, then what we will have? If we are doing policy analysis, then XIT would be assuming binary values. So XIT becomes binary if we are conducting policy analysis. All right. Now, here we are continuing with those same assumptions that we have a random sample and also that the explanatory variables are changing over time, and that there is no linear relationship amongst the explanatory variables. We are continuing with that. Now, what here we want to say is that we also want to ensure that explanatory variables are strictly exogenous. Strictly exogenous. When explanatory variables are strictly exogenous, what we want to say is that for each time period, the expected value of error, conditional upon each explanatory variable in all time period and all the unobserved effects is going to be equal to 0. All right. So how we can write that is that the expected value of the error term conditional upon the explanatory variables and the intercept is equal to 0. All right. So this is what is going to ensure the strict exogeneity. All right. Another thing that we want to see is that the variance in case of differenced errors, the variance of the differenced errors is also, we want to see that is constant. So this is basically, if you don't want to, understand it in a complicated way, what basically here we mean is that the means are 0 and the variance is constant, if we were to write it simply. And for those who would want to write it in this way, it is basically the variance of the error term conditional upon the explanatory variable is constant. Okay. Now, another condition that we want to apply here is that the differences in the errors are not correlated. All right, conditional to explanatory.
Excuse me, ma'am.
Yes, please.
In case of strictly exogenous, condition upon is intercept and
error term.
Intercept and exogenous variable are 0. Is it correct?
What?
In case of strictly exogenous, condition upon is intercept with respect to independent variable. It is a 0. Actually, this part I am not clearing properly.
Ma'am, can you
Yeah,
please explain
okay.
strictly exogenous?
Yeah, okay.
What is the meaning of strictly exogenous or exogenous?
Yeah, so in case of when we want to say that we want to talk about explanatory variables being strictly exogenous, what we want to say here is that for each time period, okay, for each time period, the expected value of the error conditional upon the explanatory variables in all time periods and the unobserved effects. Unobserved effects is given by AI is equal to 0. Is that clear now? So basically what we are saying here is that the error term, that for each time period, the expected value of error term conditional upon the explanatory variables. For here, why I did not write T is because we are saying for all time periods.
All time period.
Yeah. And what is AI representing? AI is representing the unobserved effect. Right. So we started our discussion that all our analysis in the panel data is about intercept. Right.
Yes.
Yeah. So now is this clear? So it will be, we can say that the explanatory variables are strictly exogenous only when we know that for each time period, the error term, the expected value of error terms conditional upon the explanatory variable and the unobserved effects is equal to 0. Is this clear now? So
Ma'am,
what does
what is the literal meaning of exogenous?
Exogenous is that, see, here, when we are saying this, what it means is that there is no component in the explanatory variables or in the unobserved effects which is associated with the error terms in such a way that they do not have any they do not have any interdependence and they are not correlated. So then only they will be exogenous.
Means the effects on them are somewhat from outside. Am I right?
Yes, but the error terms. Here, what we are talking about is about the error term. So there is no component in the error term. So see, when you see your equation here, in your equation here, what we are having, we have these components. Beta 1 xit like this, we have these betas, right? And we have these two terms, AI and UIT. All right. Now,
Yes.
what we want to say is that in case of what is AI going to take care of and what is UIT going to take care of? AI is the intercept term, right? And
Yes.
AI is the intercept term for each entity.
Yes, ma'am.
And AI here, because we don't have the T subscript here, that means that AI is the same for all time periods for same entity.
But for each entity, we can
For
say,
each
na?
entity, yeah.
Yes.
For
Yes.
particular entity, it is not varying with time.
Yes.
No. Yes.
All right. And
Yes.
what is mu IT, the error term? In case of mu IT, we have both the components, that is the entity component and the time component.
Yes, ma'am.
Right. Now, the things which cannot be captured by all of this, right? All of that should be here. That is what we do not know what all goes here, right?
Yes, ma'am. Because it's not
whatever
constant.
is skipped, yeah, whatever is skipped, whatever is what we have missed or what we cannot observe, all that is going here.
Yes, ma'am.
And with a component of time.
Yes,
right?
ma'am.
So in this component, if suppose in our model from these, out of these explanatory variables, if suppose, for example, say these, okay, let me take an example. Suppose that Y is the agricultural. I keep giving examples from agriculture. Even in second half also, the example will be from agricultural production only. So suppose that our dependent variable is agricultural production. Okay, this is our Y. Okay, now this is a function of, say, several independent variables or say input variables. Now, in case of those input variables, in case of agriculture, it is the land which is given by gross cropped area. Then there can be fertilizer, there can be irrigation, and there can be other factors also, mechanization and all that. Now, theoretically, we know that irrigation is one of the very important components. All right. Now, suppose that out of these variables which I have written in my model, I do not include irrigation. For example, I don't include irrigation. When I don't include irrigation, what is going to happen is that the effect of irrigation will be captured in this unobserved component.
UIT.
Yes, right. AI is time invariant. Irrigation is a time variant component. So
Yes.
AI will take care of the farmer's specific characteristics. Okay.
Yes.
But UIT will take care of things which are happening over time and changing over time. So irrigation will become a part of this, right?
Yes, ma'am.
But so with that, what is going to happen? We will not be able to say that. Now also another thing, with that, what is going to have what will be the impact on our model then?
The important element of irrigation is not taken into care of, so the value of YIT will not be correct, or it won't be reliable.
Because the error term will become bigger.
Yes, ma'am. Yes.
So what do we want to do? Basically, in all this, what do we want to do? We want to minimize the error.
Yes, ma'am.
So we want that our explanatory variables should be able to explain almost all changes that happen in the dependent variable.
Yes, ma'am.
So that is why when we want to say that these are strictly exogenous, what we want to say is we are expecting that the error term should be minimal, and that should be done in such a way that there is given these explanatory variables and this. So we are considering that all of these are given, then our error term should be, the expected value of our error term should be equal to 0. Is this clear now?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Okay. So where was I? All right. So this is first thing, and the second is that we want to also see that the variance is constant. Now variance is constant also. What does it mean? That the in case of the change in the error term, that should be constant over entities as well as over time. Now what does this component variance is constant mean? Okay, tell me one thing. Have you studied the term what is homoscedastic?
Yes, ma'am.
Yes, ma'am.
Yeah. So what is homoscedastic?
Ma'am, basically it means that the variance remains constant no matter what the values of xi are.
Yeah. So this is the second thing which we are saying here. Now, what we want to do is that we also want to see that another thing which is here, which is that the differences in the errors are also not correlated, conditional upon all explanatory variables. So how do we write that? We write that as covariance, or not, covariance of delta UIT and delta UIS conditional upon explanatory variables is equal to 0. Now, what it means is, why we are writing here T and S is in order to denote different time periods, time periods, and where we also want to say that T is not equal to S. All right. When for all the situations where T is not equal to S, there what we also want to see is the covariance between the error terms. Between the error terms, what it means is error term of one particular time period is not related to error term of another time period for all explanatory variables, conditional to all explanatory variables. Is that clear? Right? What is this component called? Yeah, can anyone tell me? See, you have already told, we have already seen what is this strictly exogenous, where we are talking about expected value of the UIT or the error term. Then we also discussed about variance is constant, where variance of the error term with conditional upon all the explanatory variables is constant, that is sigma square. This situation is known as homoscedastic or homoscedasticity. What is this called?
Ma'am, it's basically no autocorrelation.
Very good. So we are saying that there is no autocorrelation. Now, in these situations, what we want to say is that the xi's and the delta mu it's are independent. All right. And based on all these three things, we can say that xi's and mu it's, here we have seen those in our equation here. So all our xi's and the mu I t are independent and identically distributed normal random variables. You know the properties of normal distribution. You know that in case of normal distribution, the xi's are distributed such, the xi would be distributed such that the expected value of xi's or the mean is equal to 0 and standard deviation is constant, that is sigma. All right. So standard deviation. So here we are already saying that variance is sigma square. So that itself implies that standard deviation is sigma. So how does that relate here? So that shows these are following normal distribution. And when these are following normal distribution, what kind of tests we can do? We can use usual or whatever t-tests t-test and F distribution tests. T distribution as well as F distribution tests are valid. Is this clear? So if this is clear, then we will move ahead. So what does all of this talk about? This is talking about the first difference method or difference in difference, in case your data is okay. So now the last point related to the differencing data, the data is that what are the I think I can write this here itself instead of here. Yeah. So what are the drawbacks of this? Now, the drawbacks of differencing the data is, number one thing is that it cannot be used in a situation when the main or when the important explanatory variable. So I will write here drawbacks or pitfalls. Drawbacks are, number one is that if when the values of main or key explanatory variables does not vary much over time. Does not vary much over time. So in those situations, the differencing method cannot be used. Another thing is that if it is difficult to establish the strict exogeneity, or when you know that the explanatory variables, when you cannot say that explanatory variables are strictly exogenous. Exogeneity spelling is wrong. Okay. So then you cannot use. So that is a very important assumption for doing the differencing in the data. And then if one or more, if there is a problem of measurement error in one or more explanatory variables. All right. So now we go on to fixed effect model. So for the case of fixed effect model, fixed effect estimator, just the way we did in the case of Dr. Pallavi is there?
Yes, Preeti ma'am, I'm here.
Yeah, I wanted to ask you, when several people, they keep on entering or they are in the waiting room. So do I need to click on that, or what do I have to do?
No, ma'am, I'll keep clicking on that. Don't worry about
it.
Yes,
Okay.
yes, ma'am. I'll take care of the waiting room.
Yeah. Sorry. All right. So in case of fixed estimation, just the way we did in case of first differencing method also, what we are doing is basically, we are going to now yeah, fixed effect model. Now, so until now, what we were doing was, you remember when we in the first slide we were talking about the component alpha, and if we have the assumption that alpha is going to be the same, then we have the choice that we will do the pooled estimation. And if we know that this alpha is or the intercept term is different, then we have two choices, that is the fixed effect method and the random effect method. So out of those, now what we are doing is we are not assuming alpha to be same or constant. Then how do we address the concern which is in fixed effect model. So what we are going to do is here, we are going to use a transformation to remove the unobserved effect of AI or the alpha I. All right. So suppose that now we go back to our same model. So suppose we have our model here as YIT is equal to beta 1 XIT plus we have our AI plus our error term with a time subscript. All right. Now we know that for each I, that is for each entity, what we can do is we can average. We do the average. So this is the transformation that we are doing. So how we are transforming? We are going to average this equation over time. Average it over time. Okay. Now, when we are going to average it over time, what we will get is yi, okay, which is averaged over time, is equal to beta 1 xi, which is averaged over time, plus ai, which is our intercept term, plus error term, also averaged. Now, this kind, generally the fixed effect estimator is also known as the fixed effect estimation is going to give us what is also known as the within estimator. All right. Now, here what we are doing is that in this equation, the intercept term, that is the alpha, would be if suppose that here what is happening is this is called within estimator, and if we include the intercept term, if we are going to include, then that becomes in between estimator. All right. So here we are including, and therefore it is in between estimator. All right. Now, what we are going to do now is we subtract the YIT minus YI, that is the average term over time. Then we will have beta 1 here, XIT minus XI bar plus UIT minus UI bar. All right. Now, this equation is known as time demeaned data. All right. Now, this is also called the fixed effect within transformation model. Now, now here we are again going to do the same assumptions, that is there is strict exogeneity, assumption of explanatory variable.
And time demeaned means?
Yeah, time demeaned means, see, yeah, you saw here what we did. see, what we did, our model was the model was that we have dependent variable with the entity component as well as the time component. Okay, that is y, I, and t. It is given by beta 1 xit plus ai plus mu it. So here also we have the entity term and the time component. Here also we have entity component and the time component. All right.
Yes.
Now what we are doing? Now we are averaging. So how do we do that? If you want to see, I mean, nowadays we don't do all of that manually. So if suppose you have y variable here, and suppose that we have x variable here. All right. So what will you do? You will have case 1 in your data, right? In your data, you will have case 1. And for that case 1, suppose that it is case 1 is Madhya Pradesh. Okay, we want to see the explanatory variable is say the income, and dependent variable is or say this is explanatory variable is education, and dependent variable is productivity or efficiency, labor productivity. All right. So if case 1 is Madhya Pradesh, now for Madhya Pradesh, if you are noting down the data for T1, which is say, for example, the year 2001, then 2002, then 2003. All right. Suppose you have annual data for case 1, which is Madhya Pradesh. All right. And this is your labor productivity, and this is your education as one of the variables. Now, you are going to enter the data for these, right? Now, suppose that because we are talking about several entities. So suppose your case 2 is say Uttar Pradesh. Case 3 is say Orissa. Like that, you have several cases. So for each of those, for 2001, 2002, 2003, 2001, 2002, 2003, you have the data like that. Okay. Now what you are going to do? If you are going to analyze all of this, then you are basically in this first equation where you have both the components. Okay. So now what you do? You go do the average with respect to time. Okay. So for case 1, suppose that we have only 3 years data. So what I would do, I will sum it up, this summation of this divided by 3. All right. Summation y of all these values, summation yits over 3 is going to give me what? Average for this entity. And that entity is Madhya Pradesh. So this will be, instead of I, in fact, I can write I1, yi1 bar. So this, similarly, I do an average here, summation of values divided by 3. So this is going to give me y2 bar. So this is the time, what we are doing here. This is transforming the data, we are averaging over time. So when you are averaging over time, your T subscript is gone.
Yes.
All right.
Yes.
So when your T subscript is gone for this entire equation, so you are going to basically do this thing for this entire, for all of these, for yi's and for xi's also.
Yes.
Okay. Then what you are doing? Then you are differencing.
Comparing both these two.
Yes, so you are doing a differencing. Now you have yit minus the mean. All right. So this equation is going to give you time demeaned data, and then you estimate your same way as pooled OLS. All right. And when you are going to do this with this equation, when you are going to do estimation based on the pooled OLS, then that estimation basically becomes fixed effect model within transformation. All right. So this is going to give you fixed effect model within transformation. All right. Now, what are the important things to consider here? We will, of course, we have to continue with the same assumptions and same estimations, expectations related to the strict exogeneity, as well as we also want to see that the fixed effect estimator, the fixed effect estimator is going to allow for, please note this, arbitrary correlation between AI and XI. All right. And if we think that the AIs are not correlated, or there is no arbitrary correlation between AI and XIs, then what we do is, if we think that this is not the case, then that means that there is no arbitrary correlation between AI and XIs. Then we move on to random effects model. All right. And we are still left with the assumptions of fixed effect model, and we also want to see that in which situations we should use the first differencing or fixed effect model. And I would like to ask Dr. Pallavi, can we take a break now or should I continue?
Yes, ma'am. I think we should take a break now for
Okay.
tea, and we'll come back at 12.
Yeah, my tea is here, so I don't have to worry, but rest of the people have to worry.
Yes. Yes, same with me. Actually, finished some. Yes,
Yeah.
ma'am. I think, dear participants, let's take a break and we'll resume the session at 12. Ma'am, we'll continue with the meeting and yeah, we'll just resume it the way it is. We'll not stop the meeting.
So if I don't log out, is it okay?
Yes, ma'am. In fact, don't log out. Yeah, let's be here.
Yeah, because with my kind of connection and technical non-savviness, I don't think I should.
So, ma'am, I definitely recommend you to be here in the meeting. Okay. The rest of the participants will also, I think they'll remain in the meeting. We just can stop our video and just mute ourselves. That's it.
Okay.
Now we'll see you back at 12. Yeah.
Okay.
Okay.
Thank you.
Okay.
Thank you. Yeah. See you. Bye.